Okay. First, I would like to thank the organizer for giving me the opportunity to give a talk here. Oh, hello. Okay. So first, I'd like to thank the organizer for giving me the opportunity to give a talk here. So today, I would like to talk about quantum simulation of jet quenching. So first, let's see. This is the outline of the talk. So first, I will give a brief introduction to quantum computing. Then I'll highlight some applications in high energy physics and nuclear physics. And lastly, I'll talk about our recent work in in jet quenching. Okay, let's continue. This is a brief introduction to quantum computing. So on the one hand, we have these classical computers that we know. So the lowest bit of information is the classical bit, 0 or 1. Then we have the classical gates. So they are logic gates that we're familiar with. It has this deterministic nature. So you can think about this as a switch like I put it here. On the other hand, we have those quantum computers that are just being developed. So lowest bit of information is the quantum bit or qubit. It's usually implemented as a two-level quantum system. And quantum gates are inherently unitary operators. And because, as we know from quantum mechanics, they have this special feature that has superposition and entanglement. And the states only collapse when measured. So a single qubit can be represented as a block sphere, as I draw here. We have rapid development in quantum computing in the past 40 years since Richard Feynman proposed quantum computer in 1981. So we developed topologic gate in 1980s, which allow us to simulate any classical computation. Now we have the Schwarz algorithm, as we know, for factoring large numbers. And more recently, we have developed a variational quantum eigensolver and then a lot of applications in many fields have come afterwards. So currently, we're still in an age of noisy intermediate scale quanta or NISQ, where qubits and quantum operations are substantially imperfect. Nonetheless, there are a lot of hardware being developed by big corporations like Google, IBM, and many platforms such as Qiskit are being developed for developing quantum algorithm tools. And recently, this white paper, which highlights the need for quantum simulation for high energy physics. And why are we inherently interested in quantum computing? So as Richard Feynman points out, this is probably his most favorite quote, nature isn't classical. So if you want to make a simulation of nature, you better make it quantum mechanical. So as he points out, many problems are inherently quantum mechanical. And secondly, there's a vast amount of information can be coded in a many qubit state, which is impossible to compete on a classical computer. So basically, nature has this ability to do it automatically for us. And then there's a high scalability in quantum applications, as we can see in many literatures about compact encoding. And there's also a rapid progress in hardware software algorithm benchmark, particularly in the past 5 to 10 years. And then here I will talk about some applications in high energy physics and nuclear physics. So there are two main directions. One is using the so-called variational quantum eigensolver, or VQE. It's a hybrid optimization framework widely used nowadays in quantum chemistry. It has many variants. And the other is basically using the idea of quantum phase estimation, which consists of preparing, involving, Fourier transform, and measure the quantum and find the quantum state of system. And I'll highlight some recent work done by others. Oh, so before I do that, I'll briefly introduce the VQE paradigm. So it is deeply inspired by the variational principle. So basically, you can see the green color are representing the classical computer and the pink color representing the quantum computer. So we can prepare the problem on the classic computer beforehand and map the Hamiltonian to the qubits. And on the quantum computer, essentially, we have this optimization loop where in each loop, we state evolve the quantum state using some unitary ansatz of our choice, and then we make measurement at the end from the common histogram. And then we send that information to the classic computer to compute the cost function. So in the case of the origin of Linda VQE, it's a Hamiltonian expectation value basically. And then we use some classical optimizers. So there are a lot of optimizers nowadays to optimize the batch of parameters, and we send for the next optimization. So this loop will continues until some convergence is reached, and then we are able to obtain our desired quantum state. So there's a lot of similar approach as VQE type to this paradigm, such as using different ansatz like UCC ansatz and QAOE ansatz. It's been very successful in quantum chemistry. And with obtain the evolved state, we are able to make measurements of the observable directly or indirectly on the quantum circuit. So one particular applications, as you can see here, I highlight here is the quantum simulation of quantum field theory in lifelong formulation. So basically, so they were able to obtain the quantum state with the prevalence-inspired ansatz, and they have used direct and compact qubit encoding to make this happening on the real quantum computer from IBM. And then afterwards, they were able to compute the here is the form factor for the pion. And you could also use variants of VQE and a hardware efficient ansatz to get the spectrum of the meson. And there's another work for using the quantum computer to compute the 1+1 number June-Lassino model and obtain the PDF in the end, parent distribution function. And particularly like this graph is really highlighting the workflow of the VQE. And there's also a computer for VQE, which is called the quantum imaginary time evolution recently. And the idea is to use the approximation for the imaginary time evolution operator to approximate the real-time evolution. There's been some work also in the N+1 June-Lassino model. And on the other hand, besides studying the hadron properties, there's also another category, as I mentioned, the quantum simulation. So basically, we define the Hamiltonian and we encode the Hamiltonian into our desired basis. We prepare the state and then we evolve. In the end, we do some measurements. So that's the basic idea. So and this work is very interesting. It's the quantum simulation of open quantum system in high ion collisions, and it's able to simulate the link-light equation for hard probes in thermal baths. And also there's like 1 week or 2 weeks ago, there's a quantum simulation of jet quenching nuclear environment. This is a toy model demonstrating the NPL effect by including state splitting. And now, in the last part of my talk, I'll focus on our work, which is a medium-induced jet throttling in a quantum computer. So it follows a previous paper done by Barada and Zagado. And I'm working with my collaborator, Barada, and Xiaojian Du, Meijian Li. And this picture you already seen from Meijian's talk, and also this work. So we are considering a high-energy quark moving close to the light core, scattering on a dense nuclear media. So as you can see here. And the lifelong Hamiltonian, after the transformation, will become as follows when we take the quark to the massless limit. And the background field we use is the MV model. This is also already talked about. And it's a static and non-dynamical field, basically. And the correlation is achieved by using the local Gaussian distribution. And here, in this work, we're interested in a jet evolution using quantum simulation. And this is the framework that we are doing for the quantum simulation. Essentially, there are 3 stages. One is the initial state preparation, and the second stage time evolution, and then measurements. So for the initial state preparation, so we are just starting with the momentum in the 2D momentum as being 0 and 0. So that's very simple. And for time evolution, depending on how you want to compute this, it can be divided into many different steps. And each step, you have this unitary operator from the kinetic energy term, which is on the momentum space, as you can see here. You can see my mouse, right? Yeah. And then we use inverse Fourier transform to go to the persistence space and compute the field. and then we fully transform back to the momentum state. So this block will be repeated many steps. And each time when we do the field evolution, we take the data from the classical computer. So this green line is the input from the classical computer. And after the evolution, we want to measure our state. There are many different measurements protocols we can follow. There's a Hadamard test and swap test, etc. And here in this preliminary work, we will just do direct measurements. So as you can see, the quantum Fourier transform allows convenient simulation in the respective basis. And for the field evolution, so here we consider two possible cases. One is color, one is without color. So for the simplest colorful case, just with two colors, the field evolution operator can be expanded as follows. And there are different implementation of computing this. One is using exact method by the property of exponential polyvector. So basically you have a block diagonal matrix, and you have to rotate different angle at different block. And then there's also exponential matrix approximation, which you can proxy the whole matrix as a whole. And then there's also, we can do this with a linear approximation. And this is particularly interesting because it allows the separation of column position space, as I wrote here. And it's very useful to implement this because it allows for circular modularization. And the same can be happening for high order terms. And in terms of how we do this numerically, this is our basis space encoding. So for the basis space, we have a 2D momentum or position space plus 1D color space. So the total number of states here is 2 times n perp squared times nc. And for SU2, the nc will be 2. So the state will be, as you can see, the first 2n qubits are for encoding the position of momentum, and the last bit of qubit can be encoding color. So this is very natural to do. And then for the lattice, we have this periodic boundary condition. So, and everywhere is equivalent up to a periodic boundary applying a periodic function. And for convenience, we compute on the positive basis, and then we map to the real physical basis. And the lattice spacing for this in the position space will be L perp divided by N perp, and momentum spacing will be pi over L perp. And for our particular simulation, as I said, we study both with or without color, with the initial state. And for the simulation with color, we start with superposition of 2 colors. And this is very simple to do on quantum computer with the Hadamard gate. And the duration of the select median is about 10 Fermi. And we use 5 field configurations here. And 2 sets of lattice grids are being used to see the effect of lattice. So we use 10 qubit for encoding the 32 by 32 lattice, and 12 qubits to encode the 64 by 64 lattice. And we include this I regulator as I showed in the equation magnetized before. And different values, selected values of saturation scale are being used to take into consideration of the coverage and the broadening. And this is what we get from a particular simulation. So in quantum simulation, you have this number called shots. So it's how many times you fire your quantum circuit. And this is particularly intriguing because it is actually a collapse of quantum states. So it's very different from what you do for quantum mechanics. And the first row shows us the sampling noise, which is reducing as the number of shots increases. So that's basically statistical uncertainty you see here. And this particular plot shows you the configuration uncertainty. And it's important to see that our configuration uncertainty is much larger than the statistical uncertainty. So that's a good thing. And in terms of computing the observables, here we show the calculation of quenching parameter. So in this slide, I show you the colorless case. On the left, it's the result of the quenching parameter's function of saturation for the small grid. On the right, it's a result for the larger grid. As you can see, in both the econol and sub-econol limit, we're able to match with the analytical result, which is known. And for the smaller grid, you see the lattice effect at the end. So that's expected. And by removing this cutoff, you can see the momentum broadly increases. So that's understood. And I also show the 2D momentum space distribution, probability distribution down below for each of the 4 points here. And in this slide, I show you the colorful case. So we consider the SU2 color here, and we show both the econol limit and sub-econol limit. And we have to use one more qubit to encode the color, and also Phi conversion average is being used. Okay, and this particular also it's very important to know that from the MV model we have this correlation to obey. So what we do is that we cut our slack into many different layers, and by increasing the number of layers, we can see that the correlation condition is approximately satisfied, and we're able to reach the curve that I showed you. How many minutes have I had? Okay, okay. And then I'll talk about, so far you have seen the result on the simulator, and now I'll talk about what happens if we consider not only sampling noise, but also 1 qubit and 2 qubit noise. And the result isn't very good, as you can see here. So the first line you see here is using the noise model, and by taking one particular IBM backend, which is Manila, and you can see the noise really hinders our ability to compute this quantity. And then I use the customized noise model with a decreasing number of errors. So I take the first number is the 1 qubit error, and the second number is the 2 qubit error. As the number decreases, and you can see we're able to obtain what we see before with the noise-free simulation. And last slide, I will talk about some future plans. So the first thing we want to do is incorporate multiple fork sectors. For example, we want to also consider quark and gluon sector in order to study gluon absorption and emission. And secondly, we want to consider some simulation-friendly implementation of potential fields on the quantum circuit. For example, this discretization method of the potential. And that is particularly nice because then your approximation will be well controlled. And it will also really cut down the number of gates we put on the quantum computer. And then, of course, this model is very free from using different background fields, so we can investigate the effect of other medium and initial state as well. And there are also some technicality choice of using proximate to the quantum Fourier transform that might really help on a NISQ machine. And in the future, we'll also consider adding more color to simulate a more realistic QCD. Thank you very much.
Yeah, thanks for a very nice talk. So I have a question. Why do you do this mixed representation and momentum and the coordinate space? So we know that actually it's enough to know the coordinate space representation, and then the broadening it will just be kind of a Fourier transform of that. But we don't even need that. We can compute the average of the coordinate space distribution or dipole distribution, basically. So why maybe going back and forth with these Fourier transforms cost you a lot of uncertainty, noise.
Essentially, for example, in the U1 case, the kinetic energy term is diagonal on the matrix, and for the U1 case, this is covering this. So this exponential of the field operator will also be diagonal in the position space. So that's convenient to do.
Yeah, but you have to do the Fourier transform.
Yeah, the Fourier transform is not very costly.
It induces noise?
in the noise, I'm not sure, but I think mostly because we want to use the optimal basis for those two operators. Yeah.
Thanks for the interesting talk. Maybe a couple of questions actually. So for like the dimension of the system that you're simulating so far, how big do you think you have to go to get like realistic number of states? Like, is it like how large of a matrix do you think you have to extend to before you start to get towards something? And I know there are other issues with the color and whatnot that you said, but in order to get to physically enough to get something like trustable or usable in a physical case.
Okay, so in the case that I showed here, so the 32 seems to be a good lattice that we use because it covers the broadening, all aspect of the broadening. So I don't know if that answers your question. So that's about
this is
4,000 states. 4,000 states, yes.
I see. Okay. Okay, maybe a second question. Okay, I need to think about that a little more. Thanks.
Yeah,
another question maybe about your noise
yes.
correction that you did.
Oh, I haven't gone through the noise correction yet, but that's something we plan to do. Yes.
Right, but so you showed this plot about the noise model that you had that takes you pretty far away from what you wanted to get and then brings you back. And you have all these different like noise thresholds that you use, is that right? Like, is that so? How did you actually come to those values? Are those like the actual independently measured errors on the circuits, or that's just like the value you have to use in order to get agreement back to your prediction?
So except from the top line, so all the color line shows you the single qubit and 2 qubit noise only. And so I want to calibrate, see how those affect on the results. And the top line is using the IBM Manila backend. So it does not only include the single and double qubit noise, they also consider other noise such as the geometry of the setup and the readout error, etc. So that is the more realistic thing you will see on a real quantum computer. And actually I run this with a smaller grade on a real quantum computer. So the performance on par is equally bad. So, yeah.
I see.
Yes. Yeah.
Okay, thanks.
Yeah, thank you.
Any other questions? If not, then let's thank the speakers in the section.